So actually, we will like to calculate the overall E field by this disk, but we try to separate into many different ring. So for each ring, the E field generated is like this expression. So we like to try to integrate like dr from 0 to capital R, because the smallest one will be R equals to 0 for the inside, and for the outside, R will be equal to capital R. So we integrate dr from 0 to R. But so far we have dq here, so we will try to make some variable substitution to make it like we have something like dr. So next we try to do some variable substitution. So actually for this one, we hope we can sum from r equals 0 to R. And actually dq, for dq, we will introduce another charge density called the surface density. Yeah. Previously we have the linear charge density, but here we have a disk. The total charge is Q, and so it's equally distributed, uniformly distributed on this disk. So we need the surface charge density. So the SI unit will be C over meter squared. And in this way, dq will be this surface charge density multiplied by the dA. Actually, dA is the area of the ring. So suppose this ring is very narrow, dr is very small. So we have a dr is very small. So we can try to cut this ring and then try to expand it. So after we cut this yellow ring, and then we try to maybe I draw height. So we try to cut this ring and then try to expand it. So this height will be dr. And then it will become a rectangle-like shape. And actually, the width of this rectangle will be 2 pi small r. So you try to expand the ring. Yellow ring. Good. Yellow ring. Yeah. So here we have dA will be 2 pi r dr, which is the area of this rectangle. So now we can just make the substitution. So we put this one into here. So we have a sigma 2 pi r dr here. And we can try to arrange some terms. Actually, pi and pi can be cancelled. 2 and 2. Maybe we don't. Yeah. So we can just have 4 epsilon naught and then sigma z here, and then we have 2r dr like this. So we need to do this integral from 0 to capital R. So let's do the job here. So we have this term, z squared plus r squared to the 3/2 power, which is somehow like minus 3/2 power. If we just put it in the denominator. And actually 2r dr is this way, is this one. Actually z is a constant, so we can just put it there. So we can use the chain rule so that we can get minus 1/2 and then minus 1/2 power. So it's just like we have integration of x to the r power dx, which is 1/r plus 1 x r plus 1 plus constant, something like this. Which is this one. So next we can just substitute capital R and 0 in it, and then we subtract them. So we have 0, so that like this, because there is a negative 1/2. So the order of the subtraction just exchange. And then we substitute capital R into here so that we have this term. And finally, we can distribute z into here and here. So z and this one can be cancelled. And then just put c here. So finally, it is the E field generated by a charge disk. So up till now, any questions? No questions. Okay, so next, so we get the expression for the E field generated by a charge disk. And we have another assumption, like R tends to infinity, which means that this disk is infinitely large. So if R is infinitely large, this term will tend to 0. Tends to 0 as R tends to infinity. So this will become a very tiny expression. E equals to sigma over 2 epsilon naught. Actually, this is just a constant. 2 is of course a constant. And sigma is the charge density, the surface charge density of the disk. And which means that suppose this is very large, very large, which means that the E doesn't related to does not related to Z， 跟距离没有关系的，which means that the E is uniform. If we assume the charge disk is very large, for this one is still related to C. But if we assume R tends to infinity, which means that this charge disk will generate an E field which is uniform over the space. And actually, suppose this disk is very large, so that you cannot distinguish which one is the center. You cannot distinguish which one is the center. If it is large enough, you may consider this point is the center. and so which means that this is E, and also this is also E, and this is also E, all the way E, all the way sigma over 2 epsilon naught, which means that this infinitely large charge disk will generate E field which is uniform over the space. Of course, on the top side, it will all the way point to the top, and at the lower side, it will all the way point to the bottom. 就是在这个带电荷的碟子的上方，它全部的电场都是均匀指向上方啊。在这个 charge disk 的下面，所有的电场都是一样，都是指向下方，大小都一样，大小都一样。有没有问题？没有问题。Okay, so here is an application for the E-field application of the E-field, which is the inkjet printer. Inkjet printer 就是喷墨打印机啊，喷墨打印机。So actually, it's used this one is the original definition for the E-field, which means that suppose we have an E-field, and if we have a charge inside this E-field, then there will be a force, which is the electrostatic force acting on this charge. And yeah, so if this charge is positive, it will follow the E-field. If it is negative charge, the direction of the force will be opposite to the E-field. So here, we have, for example, green color ink, and we have some negative charge here. So suppose we can put some input signal so that we can try to have some green ink, try to print on the paper, and we can try to control how many charge we want to put on this green ink, so that suppose this ink go to here. Maybe I make it a little bit larger. So maybe an ink here, and then it has some negative charge, and we can just try to generate a uniform E field point to the bottom. Maybe we have some we have some this display is positive charge. This is negative charge. So the E field will all the way point to the lower side, which is uniformly, at least inside this region. So the E field point to the lower side, and in this case, there will be a force acting on the charge ink point to the top. So in this case, this ink will try to originally, if there is no charge, it will try to go straight if we just ignore the gravitational force. So it will just try to go to here. Maybe I can use green color. So this ink may go to here if there is no charge. There is no charge. But if there is some negative charge, it may go this way. This ink will go to here. So by controlling this input signal, how many charge we want to put on the green ink, then we can control. This green ink will go to where on the paper. So drop shot on the generator. G receive a charge in the charging unit C. A input signal from the computer control the charge, and thus the effect of the E field where the drop land on the paper. So this is a simple application for the E-field. So here's a sample problem. So here the diffracting plate of the inkjet printer with a superimposed coordinate axis. The inkjet dropped a mass of this one and a negative charge of Q. Enter the region between the plate, initially moving along the x-axis with the speed 18 meters per second, and the length L of each plate is 1.6 centimeter. So the plates are charged and thus produce an electric field at all points between them. Assume the field is downward directed, uniform, and downward uniform, and has a magnitude. What is the vertical deflection of the drop has at the far edge of the plate? Gravitational force is neglected. Okay. So first of all, we'd like to see how much time it takes for this drop to go through this length L. So which is pretty easy, which is T equals to the length L. The length L is 1.6 centimeter, which is 0.016 meter, and then divided by 18 meters per second. So it is which is 1/1125, and which is 8.89 times 10 to minus 4 seconds. So it's somehow like, if you still remember, K is 8.89 times 10 to the 9th equals 1/4 pi epsilon naught with some unit. But maybe it's just a coincidence or whatever. So we know the time. Here is nothing but 8.89 times 10 to the minus 4 second, and then we have F equals QE. Q is 1.5 times 10 to minus 13. E, what is E? E is this one, 1.4 times 10 to the 6th power. So, which is 1.5 times 10 to minus 13 times 1.4 times 10 to the 6th power, which is 2.1 times 10 to minus 7 Newton. So this is just like a high school physics question. So we would like to calculate the y coordinate here. The y will be nothing but 1/2 AT squared. And A is, it is F over m by the Newton's second of motion, T squared. So this is 2.1 times 10 to the minus 7. 2 times the mass is this one, 1.3 times 10 to minus 10. 1.3 times 10 to minus 10. And then, times 8.89 times 10 to the minus 4 quantity square. So y would be 0.64 millimeter. 0.64 millimeter. Any questions? Suppose this. Okay. So next one we talk about the dipole in an electric field. Dipole in an electric field. So here, previously we have talked about what is an electric dipole. Electric dipole is something like we have a positive charge and a negative charge with same amount of charge, but opposite sign, and they are kept at a very short distance. So this is called an electric dipole. And accordingly, we can also define the dipole moment P. If you still remember, P vector is QD. D is the vector. Yeah. And the magnitude is the distance between them, and also the direction is from the negative charge to the positive charge. So here, actually, if we place this magnetic dipole moment in the uniform E field, there will be a torque acting on this electric dipole. The torque is nothing but P vector cross the E field. P vector cross the E field. And for the cross product, it is just like the magnitude of themselves and then multiplied by the sine of the angle between them. Sine of the angle between them is just like if we have a P here and then E here. So this is theta. So it is just like the area of this one, of the parallelogram. And the direction is into the page by right hand rule. So you just point to the P vector and then cross to E, and then your thumb will point to the direction of the torque. So in this case, we have a P point to this side, point to the top right, and the E view point to the right. So if you use the right hand rule, we can determine that the torque on this one is pointing into the page. Torque is pointing into the page, just like this one. Which means that at this moment, this dipole will try to rotate clockwise, 会顺时针转。But actually, it will act like a simple harmonic motion. It will just something like maybe I think. You can consider this is the dipole, and then it will like if it is at rest, if there is no angular initial velocity, which means if we assume the initial angular velocity is 0, then it will like try to rotate this way and then swinging back, and then keep swinging like this back and forth. It will act like a simple harmonic motion. It's just like you have a pendulum. It's just like you have a pendulum. This one will just swinging back and forth, swinging back and forth. This one is like that case. Because if you can consider, if the E field still point to the right side, and after a while, it points this P point to the bottom right, and then you use the right hand rule, so that it will like this, pointing to the outside of the page, which means that this dipole moment will rotate clockwise. E. So it will just swinging back and forth. And this is the torque. And next one, we'll talk about the potential energy U stored in this dipole, or stored in this E field. So if we have a dipole here, and then the E field, the uniform E field, the potential energy stored there is like minus P dot E vector, P dot E vector. So for the dot product, it's somehow like we have P dot E, and then we multiply by the cosine theta. It's somehow like we have P, we have E, and then the dot product is so the cosine theta. So it's just like this one is P cosine theta. So this is theta. So the projection on the P on the E vector is the P cosine theta, the magnitude of it. So this way. And you know that, so for sine theta, actually sine theta is like this. So suppose theta is 0, which means that if the dipole has the same direction as the E field, then there will be no torque acting on it, so it just remains stable. There is no initial angular velocity. And for the cosine, it is cosine is something like this. So which means that if cosine theta is equal to 1, which means theta equal to 0, then this one is largest one, and then with the negative sign. So U is the smallest one. It's the smallest one. And if so, in this case, if the dipole moment has the same direction as the E field, then the potential energy will be the smallest case. However, if theta equals to 180 degree, then it will be the largest case, because cosine 180 degree is -1, so U will be the maximum value. So you will be somehow like swinging like 360 degree and then rotating back, something like that, which has a maximum potential energy. It's somehow like you have this pendulum. If you just swing it from here, then you have the maximum swing. But if you just put it here and then it will something like going here, here, and here. If it is here, then it is somehow like a 0 degree, which is the smallest potential energy. So far, any questions? Okay, no problem. And so we have an additional example. So a clock face has a negative point charge, negative Q to negative 12 Q. So fixed at the position of the corresponding numerals. The clock hand do not perturb the net field due to the point charge. At what time does the hour hand point in the same direction of the E field? So actually you can see a clock there, also a clock here. So actually we have a 12 number. We have 12 number. 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Something like this. And we have some charge there. So for this one we have a negative Q. For this one we have negative 2Q, and so on and so forth, until here we have a negative 12Q. So it asks you what is the E field. What is the E field at the center? At the center. Actually, you don't need to calculate the number, you just need to consider the direction of the E field. So here we can just use some cancellation. For example, if we have a negative Q here and negative 7Q here, so negative Q will generate a E field point to this side, and negative 7Q will generate a E field, E1, this is E7, onto this side. And actually the distance are the same. The distance from the charge to the center will be the same. To the center will be the same. So the only effect is the amount of charge, which means that E7 will be 7 times larger than E1. And which means that we can just cancel one of the Q, so that it will be nothing but we have a minus 6Q here, and then it generates a E field like this, which will be E. E is E7 minus E1. And likewise, if we have a negative 8Q, negative 2Q here, so minus 2Q will be cancelled, so we have E point to that side, right? So suppose we do all the job. So for 7, 8, 9, 10, 11, and 12, we will have E point to this way, this way, this way, this way, this way, and this way. All of them are with a magnitude of E. So finally, what will be the total E field, the direction of the total E field? It will point to somewhere between, not somewhere between, actually between 9 and 10, right in the middle of 9 and 10, right? Which means that for this one, the answer will be 930, 930. Any questions? Okay, so move on. So here we talk about the suppose you have you design a apparatus 设计一个仪器in which a uniform charge disk of a radius r. So this is a radius r to produce an electric field. You want to produce an electric field. So the field magnitude is most important along the central perpendicular axis. Central perpendicular axis, which means the z-axis of the disk. At the point P, at distance 2r of the disk, 2r of the disk. So this distance is 2r. So cost analysis suggests that you switch to a ring of the same outer radius r. But the inner radius is r over 2. So same outer radius, but inner radius r over 2. Assume that the ring will have the same surface charge density as the original disk. If you switch to the ring, by what percentage will you decrease the electric field? We will decrease the electric field at point P. So suppose we call this one A, we call this one B. So EA will be sigma 2 epsilon naught, and then 1 minus, so if you still remember the equation, which is E equals sigma 2 epsilon naught 1 minus Z over square root of C square plus capital R square. So this is the E field generated by the charge disk. So this one is the case. This one is the case. So we can just substitute Z equals to 2R. So you have 2R, and then 2R square will be 4R square, and then plus R square, which will be 5R square, like this. So which means that it will be like sigma over 2 epsilon naught, and then multiply by 1 minus 2 over square root of 5, like this. Okay, so next we will try to calculate the E field generated by B. So it will be like not B, the hollow part, which means that we consider the E field generated by the inside, and then we can subtract them because we cannot directly calculate the E field generated by the ring. Or this ring has a width. It's not. It is different from the one we calculated previously. For that one, that ring is very, very thin, infinitely thin. But for this one, this ring has a width of R over 2. So we calculate the hollow part first. So here we have sigma over 2 epsilon naught 1 minus Here we have R. Yeah, we have 2R, still 2R. Z is 2R, and then we have a 2R quantity square. However, this R should be R over 2 quantity square, like this. So in this case, the hollow part will generate the E field like this. This is 1 minus. Here we have a 4. We have 1 over 4. So for 1 over 4, which is 17. 17 over 16. 17 over 16. No, 17 over 4, 17 over 4, and then take the square root, we will have 17 over 2, and then we flip it, and then we have a 4 here. So this is the E field generated by the hollow part. So actually we have E hollow over EA, which is so this term and this term will be cancelled, and then we have a 1 minus 4 over square root of 17, all over 1 minus 2 over square root of 5, and then multiply by 100%, which is 28.3%. So suppose we reduce these parts, the E field will be decreased by 28.3%. 28.3%. So actually this one is pi r square. This one is pi r square minus pi r over 2 square, which is or we reduce pi over 2. So actually the reduced area is 25%. We use 25% less material to make this ring, but actually 28.3% E field will be decreased. But actually this one is not related to the original problem. So let's have a 10 minutes break.